Hello. Buenos días. Hola, clase. Hoy nosotros intentamos hacer la física. ¿Ustedes están listos? ¿Listos por hacer la física? Sí, sí. Oh, tú eres lista. Okay. Nosotros empezamos. Um, all right. So, what are we going to do today? Well, we finished talking about circular motion, and so now we're going to talk about a related topic, which is gravity. Okay. So this should be a fairly short lesson today. Definitely not going to, might be 20, 25 minutes, something like that. Okay. So we learned that the formula for the gravitational force the gravitational force is called the weight, and it's equal to the mass of the object times g. Okay? So m is the mass of the object, and g is the acceleration due to gravity the object experiences. Okay? So that's the formula for the gravitational force, also known as the weight force. So basically what we're going to do today is we are going to learn how to calculate the acceleration due to gravity. So for example, why is the Earth's acceleration due to gravity 9.8 meters per second squared? Okay. So to do that, we are going to rename the acceleration due to gravity. We're going to now call it, instead of the acceleration due to gravity, we are going to call it the gravitational field. Okay? Now, I will admit to you In in my physics education, we never referred to it as the gravitational field. We always just called it the acceleration due to gravity. So maybe I just missed the boat on that, but IB calls it the gravitational field. Okay. Um, so as we know, so the gravitational field is equivalent to the acceleration due to gravity that something is going to experience. Okay. Um, we know that the units of gravitational field are going to be, because it's the acceleration due to gravity, the units of gravitational field are meters per second squared. Okay? But when you're talking about it as a gravitational field, you tend to use different units. Okay? So the gravitational force is mg. So if we think about it, the gravitational field is force divided by mass. So if we think about gravitational fields this way, the units could be thought of as instead of meters per second squared, they could be thought of as newtons per kilogram. Okay, so this is the preferred unit of gravitational field. Okay. All right. So the gravitational field of the Earth at its surface is 9.8 meters per second squared, or we could say 9.8 newtons per kilogram. Okay. Both of those are okay, but I just want to prepare you for the IB exam where they're going to use the units newtons per kilogram for the gravitational field. Okay, so the main thing that we are going to learn about today is Newton's law of universal gravitation. Okay, Newton's law of universal gravitation. So this is what we're going to learn today. So here's the scenario. You have a mass, okay, big M. I like to use this M for the big mass. It's the Majin M from Dragon Ball Z. Okay, this mass is creating a gravitational field that the little m experiences. Okay, so we have a variable, which is the distance between the centers of the two masses, and we will call that r. All right, and so the gravitational field that the big mass produces is equal to big G, which is a constant of nature, times the size of the big mass divided by the distance between them squared. Okay? So this is our main result for today. This is called Newton's law of universal gravitation. So we can see what makes gravity strong. What makes the gravitational field strong? Well, the first thing that makes the gravitational field strong is having a lot of mass. Okay? That's why things like planets have a large gravitational field, whereas things like asteroids do not have a large gravitational field. Okay? The other thing that determines the gravitational field is how far away from the mass are you. Okay? How far away are you from the center? That's an important point. It's from the center. So we can see that the farther you are away from the object, r gets bigger, and since r is on the denominator, you're going to experience weaker and weaker gravitational fields. So for example, the gravitational field, if you are up in an airplane, you're farther away from the center of the Earth, and so the gravitational field is slightly less. Is it significantly less? No. If you go up into space, is the gravitational field you experience due to the Earth less? Yes, it is. And depending on your altitude, it may or may not be significant. Okay? Let's talk about the constant big G. Big G is called the universal. So first of all, big G is not the same thing as little g. Little g represents gravitational field. Big G represents a constant of nature, okay? So big G is equal to the universal gravitation constant and its value is 6.7 times 10 to the minus 11, and this constant has weird units, Newton meters squared per kilogram squared. Okay? So you can see, and so big G is the same for every planet. Okay, it's a constant. It's the same throughout the universe. Okay, so anything that's making a gravitational field uses the same universal gravitation constant. And so if we think about what does big G do, it basically controls the strength of gravity throughout the universe. Okay, because see how big G is on the numerator. So the larger big G is, the greater the gravitational fields are everywhere. Okay, so it controls the strength of gravity throughout the universe. I like to imagine if I was in the control room of the universe and I had a knob. I think about it like a washing machine knob. You know, one of those knobs that goes like that. And I could crank up gravity everywhere by cranking up the big G knob. You know, if you cranked it up enough, then everything would just turn into a black hole. That would be a pretty boring universe. I could crank it down, go crank it down to 0. And then if big G was equal to 0, then that would mean there would be no gravity. We could all just jump off the surface of the Earth into space, okay? Or what if we changed the sign of big G? Then we would have anti-gravity, stuff like that, okay? So big G is controlling the strength of gravity throughout the universe. Now, one of the things that you want to notice here is that big G is not actually a big number. It's times 10 to the minus 11. Okay? So that means if we were to write this not in scientific notation, we would have to move the decimal point 11 places to the left. So this is 0.0000000000067. So it's a very small number. Okay? And this is why you need something like a planet to notice its gravity. Okay? Why is this called the universal law of gravitation? It's because everything that has mass creates a gravitational field. Okay? You have mass, so therefore you create a gravitational field. So you have an M, so you create a gravitational field. But because your M is like 50 kilograms or something, once you multiply that by 6.7 times 10 to the negative 11, you're going to get a really, really small number. So the gravitational field that you create is extremely weak, but it is a real thing. Okay? For example, if you had two baseballs in outer space, and you just took the two baseballs and you just let them sit there, then the gravitational field of each baseball and the other baseball is going to slowly pull them together. Really. It would really pull them together if you're able to do this experiment in outer space. It might take a period of several days, but they would come together. So I always tell this joke. It's better in person, but I'll tell the joke again. This is my favorite joke. One of my favorite jokes that I tell is, so let's say you're on a date, okay? If you're on a date with someone, you could say, "Can you feel the force of attraction between us?" And you would be correct in saying that, right? There's a force of attraction between you and the person that you are sitting next to or across from on a date, okay? Because you have mass, so therefore you're creating a gravitational field which is pulling the other person towards you. There's a force of attraction, okay? And then if they say no, I don't feel the force of attraction between us, then guess what you could do to increase the gravitational field that they experience? You can move closer to them, make R smaller so that the denominator gets smaller, and that makes the gravitational field bigger. So you just get a little closer. You say, "Do you feel the force of attraction now?" Don't actually do that, okay? But that's my favorite joke. Okay. What else do I want to say about this? Okay. I'm just going to turn the page. Another thing that is commonly used is to not express the planet in terms of its mass. You could express it in terms of density. So if you have a spherical planet, did you guys ever learn about density? The Greek letter rho is the symbol for density. This is the Greek letter rho, R-H-O. It's a useful word if you're ever playing Scrabble. And density is the mass of the thing divided by the volume. Okay? So, all right? So the volume, if it's a spherical object, the volume is 4/3 pi r cubed. Okay? So you can use this to figure out the mass of a planet if you know the density and the radius of the planet. So we're just going to do two examples. The first one is very simple. It's what is the gravitational field at the surface of the Earth? Okay? So here's the Earth, and here is you at its surface. So basically, your distance from the center is equal to the radius of the Earth. Right? If you're standing on the surface, then your distance to the center of the Earth is the radius of the Earth. If you're up in the air, then the distance to the center is greater than the radius of the Earth. But because you're on the surface, your distance to the center is the radius of the Earth. So what is the radius of the Earth? It is 6 million meters. I use that in the circular motion lesson. Okay, so that's an approximation. That's just the number I have stored in my head. I think it's actually like 5.7 times 10 to the 6th, but I just store a nice round number in the head. The mass of the Earth is 6 times 10 to the 24th kilograms. Okay, that's another reason why I remember 6, right? Because there's 6 times 10 to the 24th. 24 is divisible by 6. It's times 10 to the 6th for the radius, so it all kind of like reinforces itself, so I can remember that really easily. Okay. Okay. We'll talk in the next lesson about how could you measure the mass of a planet. Okay. So now we plug in to the formula for gravitational field. So this is the formula for gravitational field. I plug in the universal gravitation constant, so that's going to be 6.7 times 10 to the negative 11. All right. And then the mass of the Earth, 6 times 10 to the 24th, divided by the radius of the Earth squared, 6 times 10 to the 6th quantity squared. You got to be careful about plugging these scientific notation numbers into your calculator. It's very easy to make a mistake while you're doing this. I'm going to guess that many of you will get problems on this homework or this quiz incorrect, not because you don't understand the physics of it, but because you plugged something into the calculator incorrectly. So you got to be careful. Use a lot of parentheses. Oh my gosh, Hazel. And so when I do this, I get 11 newtons per kilogram, okay? So why is that not equal to the 9.8 newtons per kilogram? It's because I was just using approximate values, okay? So I got a gravitational field that's approximately correct, okay? That's fine, whatever. So there's an example for you. Here's another example. Okay, a planet, and this one's going to be a little bit more complicated. A planet has radius, we'll say 3.5 times 10 to the 6th meters, and is made of rock of density 4,500 kilograms per cubic meter. Okay. What is the gravitational force on a, we'll say, on a 70 kilogram satellite 10 to the 6th meters above the surface? Okay. So this is a more complicated problem. So what we have here is we basically have a planet, and then there's a satellite that is above the surface. So when we think about how far is the planet or the satellite from the center, okay, so the R value is going to be actually the sum of the altitude, which is 10 to the 6th, and the radius of the planet. So it's going to be 3.5 times 10 to the 6th plus 1 times 10 to the 6th, which is going to be 4.5 times 10 to the 6th meters. So that's the distance from the center. We also have to get the mass of the planet. Okay? The mass of the planet, because I gave you the density and the size, we can use this equation to get the mass of the planet. So we're going to multiply both sides by 4/3 pi r cubed. So mass is going to be density times 4/3 pi r cubed. All right, so that's going to be 4,500 times 3.5 times 10 to the 6th cubed times 4 pi over 3. Keep in mind that the r value I'm using for in this equation is the radius of the planet. So I'm not using 4.5 times 10 to the 6th. I'm using 3.5 times 10 to the 6th. Okay? So that gives a mass of 8.1 times 10 to the 23rd kilograms. All right? So now I can figure out what is the gravitational field that the satellite experiences. So the gravitational field is big G times m over r squared. So big G is the same for all gravitation problems, 6.7 times 10 to the negative 11. The mass of the planet is 8.1 times 10 to the 23rd. And the radius we're using, we're not on the surface of the planet, so we're not using the radius of the planet. We're using the distance from of the satellite from the center of the planet, which is 4.5 times 10 to the 6th. Okay, so now I can get the gravitational field. Which is 2.7 newtons per kilogram. Okay? That is, and now that's not the actual answer to the question, because it says, what is the gravitational force on the 70 kilogram satellite? So in order to get the gravitational force, I take the mass of the object that is experiencing the gravitational field, and I multiply it by the size of the gravitational field. Okay? So the gravitational force, my actual answer, is going to be m times g. It's a 70 kilogram satellite, and the acceleration due to gravity is 2.7. Okay, so that's going to be what, 140 plus 4.9, so 145 newtons or so. Let me double check that. Oh, whoops, 189. Did my mental math wrong. Okay, so that's how you calculate gravitational field. One point that I want to make is you will often hear, if you think about astronauts, we think about astronauts as being weightless. Okay. Oh my gosh, Hazel is laying right here. See Hazel? Well, actually, you can see both of them, Hazel and Bug. And Hazel is doing some silent but deadly farts, and she is like absolutely blasting me right now. It's painful. So what was I even talking about? I'm dazed by the smell. So oh yeah, I wanted to talk about how do we feel gravity? Okay. And the answer is we feel gravity only when it pins us against something else. We feel gravity right now because we are pinned against our chairs or the ground or whatever. Okay? That is how we feel gravity. But what if I dropped you from outer space? I took you, you're in outer space, I dropped you, and you start to fall towards the Earth. Are you going to feel gravity? No, you're going to feel weightless. Okay? Why is that? Gravity is working on you, it's accelerating you, but because you're not pinned against a surface, you're not going to feel the gravity. Okay? So this is what's happening to astronauts that are in orbit. They feel weightless, not because there's no gravity, but because they're not being pinned against the ground. Okay? So if you go exactly, so there's a comment that there's no normal force to experience. We feel our weight via the normal force, okay? And so if you're in orbit in a space shuttle, there's no normal force because you are not pinned against the wall of the space shuttle, okay? Because the space shuttle is orbiting as well. So that's an important point. So gravity is kind of a different force in that sense, okay? We feel gravity when it pins us against a surface. All right, so I wanted to leave you with that thought, and I will see you in